morning, everyone. It's a great pleasure to have Francesca here today for the colloquium. So Francesca got her master's here in Bologna, and then she started traveling around the world. In 2016, I think she left for the PhD that she got for the Max Planck MPA in Munich. And then she moved to Copenhagen, to Dawn, first with a fellowship, with the Dawn Fellowship, and then with the Veni Fellowship. And 1 year ago, she moved again to Groeningen, this time, with a tenure track. So Francesca got many, many achievements. I will just mention two that I think are relevant for her talk today. She is the PI of an ALMA large program called Condor, and I guess she will talk about it today. And she's also the working group, the hierarchy working group leader for ALMA 2040. So I think if you are interested in joining the airport, or at least knowing more about that, feel free to talk to her. She will stay until tomorrow morning, so let's say this afternoon. And she's in the office 2S5, I would say. So Francesca is on you.
Thank you for this nice presentation. So good morning, everybody. It's very nice to be here again in Bologna. I want to start this colloquium with, it's working. Okay, yes. So I want to start this colloquium with a quiz. So I will ask you to raise your hand if you think that the statement that I will mention is wrong, not correct. So statement A, most massive passive galaxies are spheroids. Statement B, more than 90% of galaxies with stellar masses larger than 10 to the 9 host a stellar disk. In statement C, early type or elliptical galaxies dominate the high mass end of the galaxy mass distribution. So we think that the wrong statement is A.
There is one wrong and the other two are right? Or...
There is one wrong and the other right.
So, this
A. Okay, so just a couple of people there. B.
B.
Okay, and then C. Nobody. Okay, so the wrong statement here is A. And I know that one of the reasons for which most of you say that is B is because our intuition about galaxies and galaxy properties is driven by the Hubble timing fork. So in general, when we think about galaxies, we tend to think that galaxies, let's say, are in two separate classes. So there are the early type galaxies that have a spheroidal shape and within which stars move without regular motions. And we know that these galaxies have a very small gas fraction and almost no star formation. And then on the other end, there are the spiral galaxies that in most cases have a disks, and stars in these galaxies move into regular motions. However, in the past, we can say almost 10 years, thanks to the study of the stellar dynamics, we now know that this distinction is not valid anymore because most of the galaxies, including early type galaxies, host a stellar disk. So the fraction of galaxies that are really spheroidal is very low, is of the order of 6%. So this is to say that galaxies at redshift 0 host stellar disks. So stellar disks are ubiquitous at redshift 0. However, despite their ubiquity, we still don't know when and how galaxy disks form. And also, we still don't know which are the physical mechanisms in terms of gas accretion, impact of stellar and GN feedback, mergers, and so on, that regulate the formation, but also the growth of stellar disks. Now, the reason why I'm saying we still don't know when and how galaxy disks form is, let's say, a bit, this statement is a bit controversial in a way, because if you read the literature, you see that in the past 20 years, there have been many papers on galaxy disks and how galaxy disks evolve across cosmic time. And the general picture, or we can say the paradigm that explain the formation and evolution of galaxy disks is summarized, let's say, in this sketch here, where we can see that at a very high redshift, so redshift greater than 4, according to this paradigm, galaxy disks are not there. So if a galaxy is able to form a disk at this high redshift, these disks are transient, meaning that we expect that these disks are continuously reformed and destroyed due to the impact of physical mechanism, including feedback, continuous mergers, gas accretion, and so on. The first disks started to form at a redshift below 4, but these disks that we see at this intermediate redshift, so between 1 and 4, they have properties which are very different than the typical disks that we see at redshift 0. And the reason for this is because these disks at intermediate redshift are clumpy, thick, and turbulent. And at redshift below 1, we expect that at least the galaxies with stellar masses of the order of 10 to the 10, so typical Milky Way galaxies, they form a thin disk around the thick disk. While for more massive galaxies, what happens is that there is a morphological transformation. So galaxies transform from thick disk to more spheroidal shaped galaxies. Now, in this talk, I will show you that there are now observational evidence that challenge this paradigm that I just described. But before going into that, let me show you why this paradigm that I've just described has been used for so many years, for at least 20 years, to explain the formation and evolution of galaxy disks. So this paradigm is based on 5 observational evidence, and I will go through each of them now for the rest of the presentation. So the first evidence is that galaxies are very turbulent and dynamically hot at redshift greater than 1. So before going into this, I want to introduce some definition that I will use for the rest of the presentation. So when I talk about dynamics and kinematics of galaxies for the rest of the presentation, I refer to kinematics and dynamics derived by measuring the gas emission lines. And this is because at the moment with the current telescopes, we can study kinematics and dynamics of galaxies at high redshift, mainly using gas emission lines, with a few exceptions. And so there are 2 quantities that we can derive by measuring the kinematics of galaxies. So one is the velocity dispersion, that is basically the width of the emission line. And the velocity dispersion is related to 2 key quantities. One is the temperature of the gas within the interstellar medium. So in principle, we expect that the velocity dispersion has a value that is directly related to the temperature of the gas within the interstellar medium. However, also, at redshift 0, we see that this is not the case. So the velocity dispersion that we measure from, for instance, CO or H1 emission line is typically higher than what we expect from the temperature of the atomic or molecular gas. And this extra component is attributed to turbulent motions. So when we measure velocity dispersion, we see that these are higher than the thermal component, and we say, okay, there are turbulent motions within the interstellar medium. Now, these turbulent motions can be driven by different physical mechanisms, and we need to account for them because the dissipation of the turbulent energy happens in very few mega years, around 10 mega years. So we need to think about continuous source of energy to maintain the turbulence that we observe within the interstellar medium. The main potential candidates are energy from stellar feedback, gravitational instabilities, or accretion flows. Now, the other two quantities that I will use today are the rotation velocity, so I don't think that I need to explain this. So this is a measurement of how much the gas is rotating within the disk. And then we have the rotation support, that is the ratio between the rotation velocity and the velocity dispersion. So the ratio between these two quantities gives us information about how much the galaxy is supported by ordered versus chaotic motions. And for you as a reference, for galaxies at redshift 0, the rotation support is of the order of 10 or even higher. So galaxy disks are supported by ordered motions. Now, let's go back to the observational evidence that I was talking about before. So as I say, so there are observational evidence that the turbulence within the interstellar medium of galaxies evolve across cosmic time. And you can see this in this plot showing the velocity dispersion as a function of redshift from observational survey. That are the points here, and these shaded regions show predictions from TNG50 simulation. On the right-hand side, you see the V over sigma as a function of redshift. So what we can learn from this plot is that, okay, galaxies at high redshift are much more turbulent than galaxies at redshift 0, and they are less rotationally supported with respect to galaxies at redshift 0, and indeed they have a V over sigma ratio that are of the order of 1 at redshift greater than 4. Now, there is an important point that I want to make here, that is that these measurements that I've just shown have been derived by using the H-alpha emission line. And this is a key difference with respect to studies at redshift 0 that mainly use CO and H1 to measure the kinematics and dynamics of galaxies. Now, the H-alpha emission line is an emission line that traces the warm ionized medium. So it traces gas with typical temperature of 10 to the 4 Kelvin. So much higher than the typical cold gas that is measured at redshift 0 using CO and H1. And the key assumptions that has been done in the past to interpret the observations of H-alpha at high redshift was to say that warm and cold gas are exactly the same. So was to say that the H-alpha kinematics traces the cold gas kinematics. So this is an important information that we need to keep in mind for the rest of the talk. Now, in 2020s, there were a few studies based just on very few galaxies at redshift between 4 and 5 that use ALMA observations of the C+ emission line. Now, the C+ emission line is a tracer of multiple phases of the interstellar medium, but in general, we can say that it traces gas that is typically colder than the one traced by H-alpha. Now, based on these studies, and in half of these super small sample was based on gravitationally lensed galaxies. So based on these studies, it was found that these galaxies have V over sigma ratio of the order of 10. Now, these results were quite surprising because these galaxies for which we had the C+ kinematics were quite extreme galaxies. So they were dusty star-forming galaxies, with star formation rate of the order of 100,000 stellar masses per year, and also very massive. So this very high V over sigma ratio indicates that these galaxies were dominated by ordered motions, while we expected that based on their high star formation rate, based on their redshift, these galaxies should not even have a rotating disk. At that point, the question that I asked myself was, why do we see this difference between the value of the V over sigma that we measured and what we expect from theory, and also what is observed based on H alpha? Is it because we are just observing different galaxy populations, so it is just an observational bias? Or is it because we are using different tracers? Or is it because we are observing a different redshift? I'm saying different redshift because these purple points that you see here are very recent, are from 2025. And when I asked to myself this question was 2022. So to address these questions, I decided to, let's say, shift the focus in redshift and focus more on intermediate redshift. And this is because at intermediate redshift, there are very large samples of H alpha, of galaxies observed in H alpha. So I could make really one-to-one comparison between different samples. However, the problem is that if we want to go at intermediate redshift, so at redshift between 1 and 4, we cannot use C+. And the reason for this is an observational reason, and is related to the atmospheric transmission and the frequency coverage of ALMA. So to cover the cold gas at this intermediate redshift, we needed to use CO emission lines. And CO emission lines are typically much fainter than C+. So this means that building a sample of galaxies using CO observations is very, very challenging. So the way in which I decided to tackle this issue was to start looking into the ALMA archive. And so basically what I did was to mine in the ALMA archive and search for observations of galaxies with high data quality in terms of angular resolution, spectral resolution, and singular dynamization. I just built this sample that is called alpaca. And after 9 ALMA cycles, this sample of galaxies with high data quality for their emission lines, so we are talking about CO and C1 emission lines, were 28. And you can see them here. So since this is a sample built on ALMA archive, it is quite heterogeneous in terms of resolution. So you can see that some galaxies are very well resolved, such as this one here or this one here. Others, such as this or these, are less resolved, but in any case, they are resolved enough to estimate the rotation velocity and velocity dispersion. But before going into that, so before deriving the rotation velocity and velocity dispersion of these galaxies, I wanted to, first of all, understand whether there are disks, because, of course, I believe the rotation velocity and velocity dispersion only for the galaxies for which I know that the motions is dominated by the circular motions. Now, understanding whether a galaxy is a disk or not is quite challenging at high redshift. And you can see this in this example that shows some mock data, ALMA mock data, obtained from a simulated galaxy that is a merger in this case. So you can see In the first column, the C+ observation of this galaxy, and here you see the velocity field and the velocity dispersion field. So here there are two galaxies that are interacting, and in the other columns there are mock observations, ALMA mock observations at different resolution. So if you look at the velocity field, you see that the velocity field looks smoother and smoother when you go from high angular resolution to low resolution. And unfortunately, the smoothness of the velocity field is one of the criteria that is used to say whether a galaxy is a disk or not. And as you can see, this is not reliable because this seems to be quite smooth, while we know that is an interacting system. However, because of this, I started to think about a way to, let's say, distinguish or understand whether there is a disk or not, or whether the motions of a galaxy are dominated by ordered motions or not, by looking at the data cube and the position velocity diagram. So the position velocity diagram is basically a cut that you can do along the major or minor axis of the galaxy. And what is interesting is that if the galaxy is regularly rotating, the position velocity diagram has this peculiar shape, this S-shaped profile. So I put here an example for a galaxy at redshift 3, and you can see the counter example for a galaxy at redshift 0. So basically, I developed this tool that is called the PV split that allows for measuring the properties, the symmetrical properties of the emission of the galaxy in the position velocity diagram. And based on this, you can classify galaxies into disks and non-disks. So I applied this PV split tool on my alpaca sample, and I ended up with a subsample of 17 galaxy disks in total, for which I could reliably derive the values of the rotation velocity and velocity dispersion. Now, in this plot, you see the position of these galaxies into delta mean sequence as a function of redshift. So delta mean sequence indicates how much these galaxies deviate with respect to normal star-forming galaxies. So galaxies that are closer to the dashed line are normal star-forming galaxies, and above that are highly star-forming or star-pass galaxies. So as you can see in this case, and as I expected, based on my selection on the ALMA archive, all these galaxies are highly star-forming galaxies. Most of them are also in overdense regions, some of them even also in AGN. So this sample is a sample of, again, quite extreme galaxies. And to this sample, I then added all the measurements that I found in the literature based on the presence of high resolution observations of the cold gas kinematics. But I also selected the galaxies that have the same delta mean sequence of my sample and the same range in stellar mass, so very massive galaxies with typical stellar masses larger than 10 to the 10. And you can see this sample here that is of around 60 galaxies in total at redshift between 0 and 5. Now, let's have a look at the dynamical properties of these galaxies. So again, here you can see the plot showing velocity dispersion as a function of redshift on the left, and V over sigma as a function of redshift on the right. Now, the red shape, the red rectangular shape that you see here are measurements from the literature derived from H alpha. And I just select these samples, despite there are many samples with H alpha observations, because this was the only samples with galaxies having the same delta main sequence as the galaxies that I showed before and the same range of stellar masses. So this is the only way I found to make a one-to-one comparison between different gas tracers. So as you can see, the velocity dispersion of these galaxies, in particular at redshift between 1 and 3, are of the order of 100 kilometers per second. And the V over sigma ratio are of the order of 2, because as I say, these are extreme galaxies. So we expect in principle to have these values. Now let's put the cold gas measurements. And the cold gas measurements are this one here in blue. And as you can see, there is a systematic difference between these samples. And the difference is of the order of 3, both in terms of velocity dispersion and in terms of the velocity. So with this experiment, we basically show that there is a difference between cold and warm gas. And when we then plot the velocity dispersion in V over sigma, we have to pay attention into the tracers that we are using to measure these values. Now, at this point, the question is why there is a difference between cold and warm gas. I will list now 3 potential reasons of the difference between these two. My personal opinion is that the reason for which we see a difference is a combination of the 3 that I will show now. So the first reason for which we might see this difference is because there is a difference in the spectral resolution of the observations. Because on average, the spectral resolutions of IFU observations is worse than what we have with ALMA. The second reason is, let's say, more physical and is related to what we are really looking at when we study H-alpha kinematics. And the idea behind this is mainly inspired by what people are finding using zoom-in simulations. And in particular, you can see here, so this is a plot showing the V over sigma as a function of redshift. And let's focus on this redshift range, so greater than 4. So if we see the blue and red lines, so these are lines showing the V over sigma for the massive galaxies. And the blue is from C+, and the red is from H-alpha. So zoom-in simulations are showing that there is a difference between these two tracers. And in the specific case of Serra simulation, the difference is due to a difference in the velocity dispersion. So mainly the turbulence or the velocity dispersion from H-alpha is higher by a factor of 2 or even more than the velocity dispersion from C+. And the reason for this is related to the presence of outflow in H-alpha compared to C+. So here you can see an example of a galaxy from this simulation in C+ in H-alpha. So in both cases, there is a disk. You can see the disk here and here. But in the case of H-alpha, there is also some emission outside the disk that is coming from the outflow component. Now, at this point, the question is, what does it happen when we observe such kind of galaxy with the instruments that we have now? And to address these questions with Xian, we created some JWST IFU mock data of these galaxies from Serra simulations, and we analyze the properties of these galaxies using these mock observations to understand whether, with the typical data quality that we have now, we are able to disentangle the presence of the disk with respect to the presence of the outflow. And the answer that we get to this question is that it is not very easy. So to really distinguish the motions of the disk with respect to the motions of the outflow, even with JWST observations, we need very high signal to noise ratio. And the reason for this is because the main limitation in this case is due to a combination of angular and spectral resolution, at least for these galaxies from Sala simulations that are at redshift 6 or even higher. And finally, I want to mention also the further reason for which we can justify this difference between warm and cold gas kinematics. That is basically that there is an intrinsic difference between these two, just related to the fact that H alpha traces gas that is more diffuse than the cold gas. And this is what happens, for instance, for galaxies at redshift 0. Now, I went through the first point, and I will now go through the other point more quickly. So the second one is galaxies at high redshift are gravitationally unstable. Now, the gravitational instabilities is typically measured by, or is typically quantified by measuring the TUM parameter. That is this parameter that I put it here, that depends on the velocity dispersion, but also the rotation velocity of the galaxy. Now, according to the standard paradigm that I described at the beginning of this talk, galaxy disks at high redshift are gravitationally unstable because of the vigorous gas accretion and the continuous mergers that they have. And the instability or the presence of gravitational instabilities allows for explaining many different properties of high redshift galaxies, including, for instance, the regulation of star formation or the formation of star-forming clumps that then might migrate into the inner region and form a bulge component, or they led to the increase of turbulence and the formation of thick disk. So gravitational instabilities, let's say, are used for explaining many different aspects or many different properties of star-forming galaxies at high redshift. And the reason why they've been invoked the first time was to explain the high values of the velocity dispersion. So when the first values of the velocity dispersion using H alpha have been measured, people realized that there is no way to explain these high values of velocity dispersion by considering stellar feedback. That is the first candidate that is usually used to explain the values, the turbulent motions within galaxies. So to explain these high values of velocity dispersion, people had to include gravitational instabilities. However, we now know, based on this study that we made, we now know that there is a systematic difference between cold and warm gas. And we now know that the velocity dispersion from cold gas are lower than the one from warm gas. So this means that maybe we don't need to use gravitational instability. So we don't need to say, okay, we need the gravitational instabilities to explain the turbulent motions. And indeed, if I do an experiment using the samples that I described before, so the alpaca sample and the extended version that includes also galaxies at redshift 0, redshift 5, we see that using a very simple model, and I don't have time to go into the details of the model now, but ask me questions later if you want. But using a very simple model, we can explain the turbulent motions that we observe just by considering the injection of energy from supernova explosions. So stellar feedback seems to be sufficient to explain the turbulent motions that we observe. And Another piece of evidence in favor of, let's say, stellar feedback as a sufficient ingredient for explaining the turbulence is connected to this study that we did last year with Cecilia Bacchini, where we measured the instability within a sample of galaxy disks at high redshift. It was a quite small sample, but what we found is that 50% of the sample doesn't have any gravitational instabilities, and the galaxies at high redshift that are unstable are unstable only in a very small fraction of the gas, of the order of 30%. Now, going back to the standard paradigm, so I just discussed the first 2 points that are, let's say, observational evidence in favor of the standard paradigm based mainly on kinematics observations. The last 2 points that I will describe are mainly based on observations of the stellar component of galaxies. And this is quite interesting because it's a completely independent way to look at the same thing, but from a different perspective. So the third point is galaxies first form a stellar thick disk. So you can easily understand this because, as I said before, if you imagine the gas disk if the gas disk is thick, then stars that form from this gas are thick. So this means that in principle, if we measure the thickness of the stellar component at high redshift, we expect to see, based on this scenario, thick disk. And indeed, there are a very few studies, I would say, mainly based on HST observations that try to measure the thickness of galaxies by selecting edge-on galaxies. So they select the thickness of the stellar component, and they found that the stellar thickness at redshift between 1 and 2 is comparable to the thick disk that is found in the Milky Way and in the local spiral galaxy. Now, these studies were making very strong assumptions. So this study based on 8 edge-on samples were making a strong assumption that was to select visually galaxies that are edge-on, and then they say, okay, these galaxies are edge-on, so we assume an inclination of 90 degrees. Now you can understand from this same example here that there is a strong degeneracy between inclination and thickness. Because if a galaxy is very thin and you observe it at 80 degrees, it can appear quite thick. And this is just because it is just due to the inclination. So because of this, with Marlouche, a master student that just finished her thesis, we developed this tool that allows for fitting both for the inclination and the thickness. So the idea is that we create a model in 3D, so we have the galaxy in X, Y, and Z, and then we projected the galaxy, and we convolve with the PSF, and we make the comparison with the data. And in this case, we leave both the thickness and the inclination free to vary. We then apply this tool to a sample of galaxies from JWST, and in particular, we focus on the DOME JWST catalog. So basically, we select all galaxies that are edge-on, and we made a selection also in terms of data quality. So we just selected the one at high signal-to-noise ratio. So we studied this sample of 90 galaxies in total at redshift between 1 and 3. And what is interesting about this sample is that compared to the kinematic sample, it goes to lower stellar masses, up to 10 to the 9 stellar masses. Now, when we applied our tool to this galaxy sample, we found a distribution of the thickness that you can see here on the upper panel, and on the bottom panel, you see the ratio between the size of the galaxy and the thickness of the galaxy. So the sample that we study is the one in white and in gray, and we can make the comparison with respect to the Milky Way in red. And what we find is that the thickness of galaxies disks at high redshift are comparable to the thin disk Milky Way and to the thin disk that we observe in the local sample. So this, of course, doesn't exclude the presence of thick disks, because it might be that the thick disks are there but are too faint to be observed. But it tells us that thin disks are already present up to redshift 3 and also in low stellar mass galaxies. So the idea is that the thin gas disks are already present at high redshift, and this evidence derived from the study of the gas kinematics. They can form thin stellar disks, and this derived from the study of the thickness of adjoining galaxies. And then later on, there might be a dynamical lifting that can justify the presence of thick disk that we observe at redshift 0. I then now go briefly through the last final point, that is high redshift galaxies are clumpy and have irregular morphology. And for this, I want to show just these two plots. So these two plots show the fraction of galaxy disks as a function of redshift. The difference between these two plots is that this is from 2014, and the observations are derived using Hubble Space Telescope. And this one is from 2023, and the observations have been derived using the James Webb Telescope. So as you can see on the left-hand side, the fraction of galaxy disks at redshift 2 is lower than 0.1. While if we look at the same plot, but using JWST data, we see that the fraction of galaxy disks is quite high, up to redshift 6. And also galaxy disks dominate the galaxy populations at this redshift. So it seems that a new paradigm is emerging, and this paradigm is completely different than the one that we had before and the one that we use in the past to explain the formation and evolution of star-forming galaxies. And this new paradigm is based on the evidence of dynamically cold disks or low turbulence in high redshift galaxies. It seems that the gravitational instabilities do not play a major role, so stellar feedback is more than sufficient. And there are stellar thin disks up to redshift 3, and galaxies with a disk morphology dominate the star-forming galaxy population up to redshift 6. Now, in the first 2 points are derived, the results are based on samples of massive, highly star-forming galaxies. And one critics that is always done to me when I talk about this is, yeah, but the samples that you have been studied are extreme samples. They are starburst galaxies or very highly star-forming and with high stellar masses. That's true, it's correct, but if we extrapolate this to, let's say, more normal star-forming galaxies and low stellar masses, we should expect to see galaxies that are even less turbulent and more rotationally supported than what we observe with ALMA. And I'm showing you this here in this plot, showing the velocity dispersion again as a function of redshift. And this line is the one derived from the alpaca sample, and all the others are predictions from a model that I developed that show what we should expect from more normal star-forming galaxies. Now, to test these predictions, last year I submitted an ALMA large program that is called Condor, that is the first sample of galaxies for which we will have CO high resolution observations. And this sample of galaxies is unique because it's the first sample of main sequence star-forming galaxies. Unfortunately, due to limitations, again, in ALMA sensitivity, we could cover only the very massive ones. So these are galaxies with the typical stellar masses larger than 10 to the 10, but at least is the first sample that will allow us to really test the predictions that I showed you before. So for these samples, we have multi-wavelength data already in hand from JST, JWST, multiple CO lines. And unfortunately, I don't have any results to show based on this Condor sample, but I would like to show you the first data that is completely observed and processed for this galaxy here. So this is the CO322, and you can see the amazing resolution that we have in this case. Do I have 2 other minutes? 1, 2, okay. Okay. So in the very final part, I want to show some very, very preliminary results, and this is also to get some feedback from you. So I want to show these results on one of these 2 galaxies that are the so-called high redshift giant disks. So in the past years, there were 2 papers that came out on these galaxy disks at redshift 3 that are outlier in the mass size relation. So here you see the mass size relation, and you can see the position here. So these are disks with a diameter of around 30 kiloparsec at redshift 3. So I decided to focus on this one here because for this galaxy, I had the CO and C+ observations. What is interesting about this galaxy is that not only it is a giant disk, but it has also a rotation velocity of the order of 500 kilometers per second. So this is very peculiar because even the very massive spiral galaxies that we observe at redshift 0, they do not have these high values of the rotation velocity. And indeed, to understand or to make the connection between these giant disks and galaxies at redshift 0, I decided to select, to look into the manga sample and look at all galaxies into the manga sample with circular velocity, not rotation, but circular velocity, that is a measurement of the gravitational potential, higher than 500 kilometers per second. And by doing this selection, I ended up with a sample of early type galaxies. That is something that I expected. But what is interesting is that they are all galaxies at the center of groups and clusters. So this indicates that it is very likely that these giant disks that have been observed in the past years are connected to the central galaxies in groups and clusters that we observe at redshift 0. And the final thing that I want to say about this is that these galaxies are, in both cases, they live in very, very extreme environments because, for instance, this giant disk that I just showed is the most luminous X-ray source. It is in the core of a protocluster, and is the brightest dusty star-forming galaxy in that region. So despite this extreme environment, this galaxy was able to form a disk, or maybe was the extreme environment that drive the formation of this giant disk. I recently tried to search for this kind of galaxies into simulations, and up to now I was very unlucky because I managed to find some galaxy only in TNG cluster, but unfortunately, despite these galaxies have same stellar masses, star formation rate as my galaxies, they are not disks, and you can see it here. In these figures showing the velocity field of these galaxies. And I want to go to my conclusion because I know that it's late. So thank you very much for listening.